This macro shot of physical cables being plugged in by hand represents the manual burden visual node editors place on senior developers. You are forced to drag elements across a canvas and manually connect logic gates to build a pipeline. Relying on a human operator to physically arrange and configure every step creates serious friction when you need to rapidly deploy and scale pipeline architecture. Compare that slow visual process with the speed of modern AI IDEs like Claude or Cursor, which execute operations rapidly through text. The problem is an architectural incompatibility. Conversational LLMs output text and code. They cannot inherently parse or output the strict visual graph structures required by these node editors. This 3D architecture model illustrates the solution: a Model Context Protocol, or MCP, server. It acts as the technical bridge, translating text-based intent from the AI client into executable API logic for the n8n core. To make this translation possible, the server actively indexes the exact parameters of 1,650 workflow automation nodes. This index covers standard core components as well as highly specific community-built integrations. The LLM is absorbing strict JSON schemas, extracting precise technical constraints rather than just reading plain text documentation. By internalizing these strict schemas, the model gains the baseline structural data needed to propose valid workflow architectures. Moving beyond simple indexing, the server architecture grants the AI direct control over the execution environment through 13 n8n management tools. These tools completely bypass the human-facing GUI, mapping AI commands directly to n8n's backend API. This flowchart demonstrates how the AI uses these endpoints to autonomously construct new logic pipelines from scratch. The looping streams show the tools granting the AI authority to independently test these newly generated workflow paths. The AI reads execution logs and triggers manual commands without any human intervention. Warning tone. Granting an autonomous agent direct write access to an execution API introduces severe risk. A single malformed JSON payload from the AI will immediately crash the n8n execution environment. Unchecked API access for probabilistic models guarantees syntax errors. This architecture demands a strict safety net. This shattering containment field visualizes the core flaw of deploying LLMs in automation. They confidently hallucinate structural variables and invent non-existent API endpoints. AI models have a dangerous habit of assuming default parameters and skipping mandatory configuration fields entirely. To catch these structural errors before compilation, the protocol employs a multi-level validation strategy. This 4-layer digital sieve represents that strategy. At the top layer, Level 1 validation performs a minimal check prioritizing strictly required node fields. The protocol forces the LLM to recursively correct the error, injecting the missing string before proceeding. Down at the second layer, the node undergoes Level 2 validation. This comprehensive check utilizes a specific runtime profile to analyze the internal parameter structure. This deep scan ensures the node's internal logic aligns perfectly with the destination platform's requirements. Passing to the third layer triggers Level 3 validation. The system analyzes the entire visual graph simultaneously to verify all connected data pathways terminate correctly. This step explicitly verifies multi-output routing, checking that conditional components like if nodes connect accurately. Even after the build is complete, the protocol enforces Level 4 validation, a post-deployment monitoring stage. The system uses autonomous execution autofixing to read logs and resolve runtime errors. Integrating this multi-level validation ensures that probabilistic outputs meet deterministic requirements before they ever reach the execution API. Processing complex graph data exposes a severe constraint in the LLM context window. This dense wall of JSON illustrates transmitting an entire, fully connected workflow graph as a raw payload. It instantly exhausts your available token limits. The protocol solves this bandwidth issue by executing token-efficient Diff updates. This split screen compares the massive full transfer on the left to the highly targeted n8n update partial workflow operation on the right. The AI uses targeted pointer references to batch modify specific components without rewriting the entire file. To manipulate routing logic, the AI must explicitly define a strict 4-parameter string format within an add connection array. This targeted diffing drastically reduces system latency and API token costs. Highly efficient memory management allows the AI to rapidly scale operations to massive 50-node enterprise workflows without crashing. Utilizing autonomous agents for infrastructure logic comes with a final, non-negotiable architectural rule. This schematic visualizes a strict boundary. You must never authorize an AI to edit production workflows directly. Despite multi-level validation, probabilistic models can still generate unpredictable or destructive logic branches. You are required to silo the AI within a dedicated development environment for the build phase. Manual human verification of execution states is necessary prior to pushing the code live. The AI is an incredibly powerful architect, but human engineers must remain the final gatekeepers for production data. This assembling digital blueprint represents the complete technical stack we've covered today, starting with comprehensive n8n node indexing. We examined the implementation of strict deterministic validation barriers to control hallucinations. We detailed the necessity of token-optimized diffs to manage context window limitations efficiently. This combined architecture successfully eliminates the friction between text-based AI IDEs and visual execution platforms. Senior developers no longer waste time manually dragging nodes or digging through parameter documentation. This protocol shifts the engineer's role from a manual builder to a high-level systems orchestrator. If this architecture overview blew your mind, hit subscribe.